induced liquefaction risk by induced partial saturation. It is a novel ground improvement technique concept that we have recently developed. This is my presentation outline. I'll be talking about a little bit about the mechanism, factor affecting liquefaction, effect of liquefaction, and what is the existing status about the ground improvement against liquefaction, and what is the research gap, and I'll introduce the partial saturation concept. Based on this research, I'll be discussing about few research outcomes and finally concluding remarks. So this is the overall presentation outline. Just have a look at this particular slide. What is really happening when you have an earthquake? So look at the left side of your screen. This is what the typical scenario what is happening during the time of earthquake. Suppose if you have a structure which is built over a loose sandy soil, loose soil deposit. Your soil is under saturated condition. When earthquake comes, you know the impact of earthquake, it will introduce the vibration on the ground. And the vibration will propagate through the medium and it will hit the structure, and the structure is subjected to vibration. And so your structure is subjected to motion, to and fro motion. Thereby, your supporting system soil is subjected to high vibration. During the process of vibration, the vibration is taking instantly. I mean, your saturated soil dissipation of pore pressure will build with respect to increasing vibration. To build a pore pressure, you are not having enough space to dissipate. So the build pore pressure will try to destroy the soil connection by the way of developing pore pressure. If the pore pressure development is more than the effective stress of the soil become a loosened state and it will act as a single body. Then it will float in a water. So complete the shear strength of the soil is going to be looser. So this is the concept of liquefaction. Once that has happened, so whatever the loading system you have on the top of the soil, you simply go down, leads to have a severe structural damages or severe problem to the structures in terms of serviceability. So this particular concept, basically we can make out in terms of available shear strength in the soil mass. So as we are all very well known, available shear strength is C plus sigma tan phi, where C is the cohesive force. When the cohesive force is predominant, then the development of pore pressure will be less. So we no need to worry about the concept of liquefaction or the response of liquefaction plus P. But however, when you are dealing with the soil which is having poor cohesive resistance, and where you are talking about granular soil and especially fine silty sandy soil, where you have a very fine particles and the level of permeability is very, very low. So when the pore pressure is enormously built, so the built pore pressure will not dissipate. So the developed pore pressure is, when it reaches to close to the available shear strength, or that is in terms of the vertical overburden pressure, or the built pore pressure is more than the effective overburden pressure, then you will be having a problem. Soil will float as like a soft liquid being. So this is what it is happening. Loose saturated soil during the ground shaking tends to compact and decrease the volume. No drainage is taking place, so pore pressure is increased, initiated the liquefaction. So conceptually, you can see here, this is what it is happening in the real field. You are vibrating, so the soil grains are, before earthquake, it is having more connections. So the shear strength and mobilization is basically with respect to connecting between the particles. So once the particles are highly connected, then you have a more resistance. But that connection will be destroyed by the shaking, and that shaking in the help of developing pore pressure. So we have issues related with the slope failure, bearing capacity loss, and dislocation of retaining structure, settlement related aspects for the structure. These are the induced problems with respect to liquefaction. So these are some of the classical liquefaction induced failures you might have already come across in many places. more than 200 buildings tilted or excessively settled as a result of liquefaction during the 7.5 magnitude 1964 Nikata earthquake in Japan. And such failures are recognized as the liquefaction induced bearing capacity. You can see here these buildings simply it is tilted or rotated, and structural distresses are very, very minimal. So it's only problem related with the supporting soil liquefaction aspects. So buildings simply settle down or tilted as like here what you have seen. So it is a very highly dangerous one, especially during the process of liquefaction. So hello,
Yes, sir.
sorry,
Yeah, it's okay, sir. The presentation also has to be shared, sir.
yeah, is it visible?
Uh, yes, sir. But it is not in the slideshow. Yes. Yes, sir.
Okay, so just I was showing these figures, the problem related with liquefaction. Just have a look at this overall scenario about seismic event. Our Indian standard IS 1893 was revised in 2020. So India's coastline almost close to 7,500 kilometers, which signifies a very high seismic hazardous, and especially for where we have a more liquefaction risk, and more than 50% of these areas are vulnerable to liquefaction activities. According to the outcomes of microzonation map, including the liquefaction flood zone, 63 cities are vulnerable to have a more liquefaction. So, so wherever we consider about the soil under saturated condition, where you are having poor grain soil with less compactness, less density, will prone to have more liquefaction aspects. So already we witnessed these liquefaction impact on many of our structures in India, especially during the huge earthquake. We noticed several liquefaction induced failures on the structure, and there is a need for seeing about the aspects of liquefaction, and we need to have a mitigation methods. As of now, we have several ground improvement techniques to mitigate the soil by using simple improvement techniques. So these are some of the traditional methods we often use in the site to improve the capacity of the soil, either doing the dynamic compaction, vibro deep compaction, grouting, stone column, or foundation replacement, chemical stabilization. These are some of the existing methods we often practice in the field. So these existing methods are having a lot of limitations. Like the deep soil mixing and grouting, basically it is a cement-based box emitting almost 1,47 tons of CO2 and consuming almost 11,74,000 gigajoule of energy. So how much energy we are consuming and how much CO2 emission that we are producing for a cement-based method of construction, and especially using soil compaction. And comparative analysis shows that the alternative method like constructing reinforced concrete structure, diaphragm wall kind of thing, or have a higher energy consumption compared to the cement-based soil mixing. And there are several environmental challenges that we are facing with respect to the conventional material, and we have a limited field applications. It's a non-biodegradable material and inappropriate for significant ground cuts, and vulnerability to high pH, ammonia byproduct, low economical feasibility, high sensitivity to water, and severe hydrogen swelling. These are some of the concerns with respect to existing methods. So the challenges what we have, the possibility of impact on the surrounding structure. Suppose you rely on this existing method. The existing method is more suitable where we are talking about greenfield project, but the project is related to an existing building. These methods are having a high concern, and these methods are having more construction cost and the risk of polluting the surrounding environment, polluting the body, water bodies as well, not applicable to existing. This is significant. We are using significant natural resources. So we need to look at an alternative method to replace the so-called existing method, and how we can able to strengthen the soil against the liquefaction mechanism. That is the basic principle behind this particular study, in this particular research. And we have done in line with that, we have done the research, and we have developed a new method. We have developed a new method called induced partial saturation. Just to have a look at this, the mitigation of earthquake-induced liquefaction risk by induced partial saturation. So basically, we want to. The problem is very well known. The problem is occurring where you have a fully saturated soil. To some extent, if you are able to reduce the degree of saturation, the level of water content in soil mass, you are trying to reduce the developing pore pressure during the time of earthquake, and thereby the development of pore pressure is reduced and the chance for leakage be reduced. So this is a simple concept overall. But how are we going to introduce the reduction in water content soil mass or reducing degree of saturation in soil mass is completely with respect to this particular concept. So all these destructive methods, we have a lot of difficulties. We have a lot of environmental challenges. We have a lot of CO2 emission, time-consuming process, cost-consuming process. So we need to look at an alternative. So there are several ways to bring out induced partial saturation in the soil. Either you can do direct air injection, thereby you can reduce some water can be replaced by water, yeah. So we can assume that your water system is reduced to partially saturated state. Or you can use microbes induced microbes can emit gases, so thereby you can able to maintain partial saturation, or you can select some sort of chemicals which can also reduce the degree of saturation soil, or you can go with the electrolysis process. So in this particular talk, I'll be talking about only air injection and microbial induced partial saturation. So let me briefly explain about the concept, what is really happening. So look at here the schematic diagram, what you are seeing here. Suppose you have a liquefiable soil. So liquefiable soil, you know that your resistance is supposed to be less, SPT value is less than 10, and this soil is, when it is being subjected to earthquake, having a loosen its shear strength. So conceptually, you look at here this diagram, what is happening, it is a fully saturated soil mass, where we are trying to introduce gas particles in it. So this may be the particles induced by biogas or externally induced water. So as we know that the soil element is subjected to all around confining stress sigma 3, it is a constant with respect to the direction. When the stress being increased, when you are using with the microbial process, you are basically identifying the species, which the species will grow on the soil on its own and produce the biogases. So you need to have a control system such a way that how much, what kind of species you need to use for a particular soil system, and what will be the production level with respect to time. All these things you need to micro level you need to do the analysis. So assume that bio air bubbles have been introduced by this bacteria, this species, and this white spot what you are seeing is accumulated air bubbles infused by microbes. So these are accumulated within the soil skeleton, and this introduction of these air bubbles will replace amount of water, so the water becomes fully saturated state to partially saturated state. So this is a concept about growing bacteria and developing. The second method is air injection method. So you can directly have an air injection below the ground, control the air injection such a way that the air injection bubbles will have accumulated within the soil skeleton system, and the amount of air injection whatever we introduce on the soil system will replace the water equally. So this will bring to the partially saturated state. So these are the two systems what we have developed in our laboratory. Okay. So the liquefaction risk mitigation plan and design execution is our main focus. And the introduction of air or gas into the soil, how this is mitigating the liquefaction accessibility. And finally, the environment friendly economical application with respect to the nearby structure is a very, very favorable aspects with respect to existing buildings. And considering all these favorable aspects with respect to induced partial saturation, so this method can be treated as one of the best method to ensure about liquefaction mitigation. Just to have a look at this conceptual formulation with respect to liquefaction mitigation or induced partial saturation. What is really happening during the time of induced partial saturation under earthquake condition? You look at here, this is the overall scenario with respect to the pore pressure development with the degree of saturation. The parameter B is representing the level of degree of saturation. If it is 1, it has been treated as a fully saturated state. So we have a problem with only fully saturated soil mass. And if the value is negligible component, this is taken as a dry sample, no water influence effect on the soil. And between these two levels, we have a partial saturation when the B is less than 1, where we are trying to provide activated air bubbles, and thereby we are making the soil from fully saturated state to partially saturated state, where we are bringing into the influence of air bubbles infused system on this. Look at the microbial, microstructural point of view, and this is the one what we are considering with respect to the schematic view, what explanation diagram what is being given here. This is in terms of the real field problem what you are looking here. So you have a water content at some depth. You know that beyond that you will have a fully saturated soil. At some depth you will be having a partially saturated soil. And when you see here the response with respect to partially saturated soil, schematically when you exclude the sample from here, the partially saturated soil you will be having accumulated air bubbles within the soil skeleton. So this accumulated air bubbles is the one going to help for your liquefaction operation. So I don't want to go much on this technicality. Just you try to understand the concept, why, how it is working, and what is the significance of the accumulated air bubbles influence. So basically, the accumulated induced air bubbles is going to have. Can you please wait for 1 minute? The noise is too much. Just 1 minute, I will ask you to stop. Sorry, am I audible?
Yes, sir.
Okay. I hope the slide is visible.
Yes, sir.
Okay. Yes, this is the basic theoretical mechanism, how it is working. Just I will emphasize what is happening really with respect to the accumulated air bubble. So before introducing the accumulated air bubble, it is a fully saturated soil mass. So whenever you increase the dynamic force, this is delta sigma is introduced vertical stress. It's maybe under static condition or dynamic condition. So this is the field condition where the sample, your soil is subjected to confining stress sigma 3. So over and above, whenever you have additional stress, This will try to increase the pore pressure. So when pore pressure is increased, the increased pore pressure will try to push on the soil grains. So thereby the soil grains are reduce its contact surface. So it's basically floating in water. So this is the one what is happening in the site or in the field during the earthquake process. But the advantage of introducing air bubbles, what is going to be considered. So air bubbles are basically once it is being introduced in the soil system, this will try to avoid the movement between the soil particles because air bubble will have a compressibility more than water. So this will absorb the vibrations energy and it will try to come and the pore pressure is going to be reduced. So this is one aspect. The second aspect, the infused air bubble will have a contracting effect with respect to the earthquake forces. So these are the two important. Bulk modulus of the system will be more. So after introducing the air bubble, the bulk modulus of the system is going to more compressibility within the soil system, thereby the development of pore pressure will be reduced. That help us to. So this is basically the theoretical background has been explained in terms of index properties and the compressibility with respect to the air bubble, accumulated air bubble influence on system. So basically, we are concerned with the compressibility modulus. Just I'll skip this all literature background. And these are the objectives related with that particular problem. So this is a basic methodology what we have. Direct air injection. Which is more prone to have a liquefaction is a boundary denoted by a red line. The gradation chart. When it falls within this range, so you'll have a more liquefaction risk. Boundary. The soil is basically a poorly graded soil, and according to this one we have taken, and we started with the microbial induced partial saturations. Say with that, this particular bacteria should have a growth within the soil. Gas to make accumulated air bubbles with tank about 40 hours, they got the maximum growth, and accordingly this has the maximum was 76.5 in US observed, and this is a complete conformity test for the nitrate radicals. And the Pseudomonas bacteria, basically we are intent to get the nitrogen gas properties with respect to nitrogen gas. It is chemically inert material, inert gas, non-combustible gas, and non-green gas. So greenhouse gas. So these are the some. That's why we have gone with the nitrogen gas. So because since the gas is being mixed with such a way that water quality is supposed to be ensured. So in order here, the Pseudomonas bacteria was mixed, and if you have a closer look, the bubbles you can. So 20 we have increased the temperature at 30 to 60 days. We have monitored, and and 47 47-degree temperature with 30 study. We identified we need to have a temperature variation is affecting the formation of and considering our Indian scenario, it is a very expected temperature. Species is very much working to produce nitrogen gas. So that is what, and you can see here. So basically, we are trying to make and the amount of initial nitrate concentration with respect to the species what we have considered. The water is being replaced on the soil, and what will be the corresponding degree of saturation that we theoretically the initial pH and final pH with respect to the variation, because we have complete the formation, making changes over in the soil. So consistency. There is a slight variation with increase in number nitrogen concentration. This from this process, and we have also seen the microstructural calcium precipitation, calcium carbonate precipitation. So as your the binding property of the structure, soil grain. So thereby, we are not very keen to have such a CaCO3 precipitation to have a strength improvement. So this is expected auxiliary benefits with respect to microbial induced. Traction apparatus where we want to introduce the component of microbes, how the air is, what will be the displaced water, all we have modified this complete setup to have a measurement. We have quantified the replaced water from the water volume. We have more air bubbles introduced in the system. Liquefaction system in the mold, such a way that the uniform density has been maintained. Introduce the liquefaction related problem. So this here we normally consider 30% relative density with the very loose state to medium dense state up to 40-60% we have considered. So this compactive energy is changing with respect to the relative density. So relative density 20 is the bottom, relative density 60 is at the top. So the energy is also varying according to the required compactness in the soil. So using this particular principle, we have adapted what type of relative density that you wanted to have. So that is what we have developed a device for that. So it is very simple. The degree of saturation basically we wanted to obtain. It is not a direct measurable quantity from this exercise, from this experimental study. But this degree of saturation basically we can measure through the displaced pore pressure or displaced water. So from that, we made a correlation with respect to the parameter, the so-called parameter. B is the parameter, Sumton parameter, which denotes about the degree of saturation. When B is close to 1, the soil is fully saturated state. And B is less than 1, you have air bubbles within that, so the degree of saturation is going to be reduced. So you can see here, if the degree of saturation is less than 80%, almost the effect of saturation is not a significant one. But when the degree of saturation is moves from 80 to 100, you can see here you have a huge variation in the pressure variation, pore pressure variation. So the pore pressure parameter is a direct measurement with respect to the pore pressure development. If you deal with in this range, 80 to 100%, and definitely you can expect a liquefaction risk because the pore pressure parameter is very high, and accordingly the developed pore pressure will be very high. So pore pressure parameter and pore pressure development is direct relation. If B is high, pore pressure will be high. B is low, pore pressure will be low. If B is low, pore pressure low, then chance for liquefaction will be almost insignificant. So we basically worried about this area 80 to 100. So we want to work on this area where you need to introduce the calculated air bubbles to see the response with respect to that. So this is the symbol with respect to the bulk modulus. The variation has been developed, and all we brought into the elastic constant, both G and mu, shear modulus and Poisson's ratio of the soil with respect to the compressibility characteristics. And from that, we can able to theoretically obtain the degree of saturation. So finally, an equation has been developed with respect to the degree of saturation, where you have a known parameter. You are only playing with a known parameter. In terms of the calculated so-called displaced water, you can be able to obtain the value of C. Compressibility constant is very well known to you. Air compressibility is always taken as a constant, and CW is also known. So these are the known parameter what you have considered. After obtaining this, you can look at here pore pressure coefficient and degree of saturation. So this is the available theoretical establishment within pore pressure coefficient and degree of saturation. Whereas using this particular equation, this is the equation we have developed, and you look at the variation. This is almost coincide with the existing method, so it is having a more reliability to use this theoretical equation to obtain the value. So these are the basic study with respect to the principle involved with partial induced partial saturation, how the partial saturation is working to mitigate the liquefaction risk. Now let us move on to the actual problem. So liquefaction is a critical one, as I highlighted in the beginning. So how do we assess? How do we quantify the liquefaction? So there are two criteria described by Seed and Lee. One is the initial liquefaction and full liquefaction. This is with respect to the two important criteria. One is the stress criteria, other one is strain. The stress criteria says that the pore water pressure ratio or pore pressure ratio is defined as the excess pore pressure developed during the time of earthquake to the initial confining pressure, that is your sigma 3 or sigma c. If this ratio, the developed pore pressure ratio over the available confining pressure, if this reaches to more than 0.9, then you will have a chance for liquefaction. So this is the stress criteria. So coming to the strain criteria, the double amplitude axial strain, when it is more than 5%, then you will have a risk for liquefaction. So these are the two guidelines based on the stress and strain. We can quantify where we are exactly getting the liquefaction risk in the soil. So this schematically you can look at here. So where you are looking about the double amplitude axial strain, when it reaches to 5%, then you have a problem related to liquefaction. When the developed pore pressure parameter or the pore water pressure ratio reaches more than 0.9, then you'll have a problem. So this can be introduced by two mechanics in the laboratory, two ways. One is a flow liquefaction, another one cyclic mobility liquefaction. So flow liquefaction is not normally induced through monotonic or cyclic loading. So static shear stress recurs to equilibrium condition when it is contained state. The shear your flow liquefaction can be introduced. So this is a rapid loss of strength leading to a flow and unlimited strains and steady state condition. Whereas cyclic mobility, it is a flying stress less than the steady state shear strain, normally induced through the cyclic loading. So again, it is a loss of shear strain, the accumulating axial strain up to the specific number of cycles, the uniform EVT stress is applied. So basically, we have gone with just to have a critical state, what is happening. As you know that this is the normal response to what you are considering under cyclic flow. So this is a typical hello.
Sir, yes, sir.
Am I audible?
Yes, sir. Yes, you're audible, sir. Sir?
Hello, hello.
Yeah, you are audible, sir.
Okay, okay, fine. So this is a typical stress path when you're considering. And so through this mechanism, how we are going to attain this critical state is explained here. We need to obtain two parameters. One is cyclic stress ratio, then one is cyclic resistance ratio. So basically, the liquefaction factor of safety is explained. I mean, obtained through this ratio of CRR by CS. The code. Also, this method was developed by Seed and Retrieve in 1971. This method is very popular. Using this method, you can able to get the CSR ratio. By using this concept, you can able to get after getting the CRR and CSR, you can able to get the factor of safety. Good parameter that we need to introduce on the soil to make the soil such a way that it is untreated soil. Pressure and corresponding relative density, we have gone with the 30, 40, 60. And with respect to the classical way of approaching this particular problem in fracture test. We have calculated, we have taken this selection is resembling the Bernoulli, Uttarvasi, and Indo-Burma. 7.2 magnitude earthquake. CSR, and the CSR we have taken from point the so-called very popular earthquake occurred. Pore pressure on your sample. So we did relative density 30 resembles the sample as more white space, means in loose state, so under saturated condition with a relative density of 30, even having a small magnitude of earthquake, but soil supposed to have a liquefaction. That is a basic concept. So look at here the sustained curve, what you are seeing, and treated soils are behaving better than untreated soil. That's the first observation. And when the confining stress is increased, obviously the failure stress is also going to increase. It's a very common observation with respect to your soil response under undrained condition. But the other point is, the second plot is very much important for us. How the excess pore pressure is developed. Pore pressure is developed with respect to axial strain that has been plotted here. You can see here the untreated soil or solid lines are reaching close to 0.9, the pore water pressure ratio. RU values reaching close to 0.9. With the increasing axial strain, even 2% itself, it has reaches to the failure state. So this, as witnessed, clearly shows that 30% of relative density subjected to your earthquake motion corresponding to 0.2 CSR value. We introduce, starting the liquefaction process, even having an axial strain of within 2%. So it is very common. So you have a risk of liquefaction. And the soils being treated, here treated means we have introduced microns, pseudomonas microns, that has produced air bubbles, accumulated air bubbles. Because of the accumulated air bubbles, your water pore pressure parameter ratio is significantly reduced. Even after having a larger strain, the pore pressure parameter is almost constant, but it is not reaches beyond 0.5 ratio. So that shows very clearly the soil is not having a liquefaction resistance. So that has been explained with the stress path method here. So increasing relative density, it's very obvious. Increasing relative density will have more strength, but the increasing relative density may also go for a liquefaction risk when the magnitude of earthquake is increased. So that is what you are seeing here. You have a risk even with respect to increasing relative density. This is with respect to 60% relative density. So basically, you are expecting the failure after having larger strain rate than the poor soil, but 60% relative density is also subjected to liquefaction, where you are considering higher magnitude of earthquake. So this basic study what we did with only with respect to static analysis is, we have not inputted the earthquake, the so-called CSR ratio here, but only in terms of the pore pressure developed under undrained condition or considering the different relative density. So you can clearly see in these two pictures, we are trying to highlight what is happening with respect to degree of saturation. So the degree of saturation when it's 90%, where the undrained shear strength ratio we have a very high, and there is a variation with respect to the so-called relative density and keeping a same confining pressure. So there is a small changes, small variations on with respect to the relative density changes. And now we can look at here, if the degree of saturation, when it is increased from 96% onwards, you have a very high pore pressure development. So if anything goes beyond certain level, you may have a risk with respect to this region also. But since we have done only static analysis, we are not very sure about the failure mechanism. But it is very definite that if your degree of saturation goes beyond 96%, you can definitely expect such kind of failure mechanism even under static state. So this we have developed with instability lines in the liquefaction potential index. That shows very clearly you have risk with respect to increase in degree of saturation. So let us do the dynamic analysis. Maybe we can have just 5 minutes of discussion. So far what you have seen. If you have any questions, you can come up with your question. Hello? Hello? Am I audible?
Yes, sir. Yes, sir. Audible, sir.
Just we can have just a 5 minutes break.
Yes, sir.
Break means we can have a discussion.
Okay, shall we ask the participants to join by 2:25 in that case, sir?
No. We can continue. If at all they have any questions, we can have a discussion, then I'll continue. Let us not break the session.
Okay, sir.
Continue the session. Just for a discussion, I can break for 5 minutes.
Okay, yes, sir.
Any questions?
Yes, Mr. Syed, if you have any questions, you can ask him.
Otherwise, you ask them to type in the chat box. You can read the question. I can answer.
Mr. Syed, you have any questions? Participants, if you have any questions, you can either ask or you can just type your question in the chat box. Mr. Syed, are you talking?
Good afternoon, sir.
Yeah, please.
Recently we came across this stone column option. Like this has been there, I
Yes.
think, since so many. Like, how feasible is this option that you opted, with, like this introduction of this bacteria, and to implement this in the site, sir?
Okay. So as of now, the development method we have not implemented in the field. So that is what our next stage of we want to implement in the field and we look at the feasibility study in
Okay.
overall in all the aspects. But we have done a model level study. In the laboratory, we introduced everything. I mean, what you're looking is only based on the cyclic actual apparatus outcome. We
Okay.
have expected the studies to real shake table test actually we are doing it. And
Oh.
we have developed certain models, devices to maintain a uniform degree of saturation. And there are several challenges are involved in this method. So as of now, we don't have any standard procedure. That is our ultimate aim. We want to develop a system for this.
Okay, sir.
Of
Thank
course,
you, sir.
fielded, we have a lot of challenges we need to overcome.
Yeah, thank you, sir. Actually, I'm your student. I'm 2015 batch of N83G, sir.
Oh,
MD
great.
structure.
Oh,
Glad to
that's
meet you here.
okay, okay, good, nice to meet you.
Thank you, sir.
Any other questions? Okay, then I'll continue. In this slide, what you are looking is pertaining to the actual earthquake data, cyclic analysis. The figure 1, this is pertaining to a per pressure ratio with the number of cycles. And basically, we have gone through, gone down with the further low relative density 20% and taken as a confining pressure of 75. This is corresponding to earthquake CSR ratio, cyclic stress ratio of 0.2, and this is simulating close to the field earthquake condition what I have highlighted in the previous slide. So now we are trying to introduce the real earthquake force on the soil. And the untreated soil specimen is almost close to 100% degree of saturation. And with respect to this cyclic mobility, we noticed what is happening during the process of the CSR corresponding to 0.2. And this has been inputted in the cyclic triaxial apparatus, and we measured the failure mechanism. So look at here, the pore pressure ratio, RU values reaches almost close to 0.9 after having a number of cycles of 6. So that means that 20% relative density soil under fully saturated condition is prone to liquefy, even having a small number of cycles. So 5, 6 and all, it's nothing, even if that happened within 2 seconds when you're talking about the magnitude of earthquake concern. So 20% relative density soil is having more prone to have a liquefaction. So even having a small number of 6 cycles, we are expecting this one. The same soil, when it's being treated, what you are looking at the bottom, the development of pore pressure reaches maximum of 0.5, even having a number of cycles close to 50 or 60. And thereafter, even the number of cycles are increased, the pore pressure ratio is maintained as constant rate. It's never been increased. That is a clear case where we can see that it is not, the soil is nowhere going to have a liquefaction with the influence of increasing number of cycles. So it has maintained maximum of 0.5%, 0.5 ratio as a pore pressure, so no chance for liquefaction. So this is the first criteria with respect to stress condition. And look at the strain criteria. The untreated sample reaches the maximum. I mean, even having a 6th cycle itself, it reaches to the double amplitude strain rate close to 6.2%. That means, according to the criteria, it has reaches to the liquefiable state. So, whereas the same treated soil having a number of cycles increased, and you can look at the variation of double amplitude, even it does not reaches beyond 0.47 or 4.25 or 27. So it is maintaining a consistency double amplitude ratio. So the soil is very well within the liquefiable limit. So this observation is noticed. So basically from 99 is the degree of saturation what we have considered. This has been treated, that means the micro-induced accumulated air bubbles replaced water reaches to a degree of saturation close to 93%. So the reduction of almost close to 5.3% reaches a great improvement with respect to the liquefaction resistance. This is the first observation, and correspondingly, this has been plotted in the spheric loop, and where it has been witnessed great improvement with respect to increasing, reducing the degree of saturation in the soil. And this further extended with the higher level, increasing relative density and increasing confining pressure and increasing magnitude. So low relative density, low confining pressure, and less magnitude of earthquake is also risk. And a high increasing density, 30 is not really high. Again, it is a loose state. But increasing confining pressure will be a favorable property against the liquefaction. So suppose you are going deeper and deeper from the ground surface, your effective overburden pressure will be more. This is basically called effective overburden pressure. If the effective overburden pressure is more, then the development of pore pressure is supposed to be much higher than the effective overburden to initiate the liquefaction process. So deeper the depth, you have less risk against liquefaction. Shallow depth is always dangerous. So normally, typically, if you take a top 5 meter when it is saturated, you are dealing with the saturated soil, you have more risk for liquefaction. In that scenario, we are increasing the degree of saturation. We are increasing the relative density, and we are increasing the confining pressure, and we are also increasing the magnitude, earthquake magnitude. We are looking what is happening for such a scenario. So the earlier case, 20% relative density, it has liquefied at the number of cycle at 6. Now increasing relative density is just corresponding the liquefaction problem up to 9 cycle, but it is liquefied after reaching the number of cycles 9. So even double amplitude also you can look at here, it is increased to 6 to 8. Whereas if you are considering the treated soil, where you are maintaining the degree of saturation reduced to 93.1, and where you are reaching a maximum value of 0.7, even after having a consistency, almost a 6th cycle itself, you are reaching to 0.7, and after that, it is almost a constant value. And as well, the double amplitude strain also, you look at here, it is not reached beyond 2%, even having a increasing number of cycle up to 30. So that shows very clearly, increasing relative density is favorable. It is pushing the risk to certain time extra, but definitely it is also happening. So you need to have an improvement. So that is what we call it as induced partial saturation. So again, it has been explained in terms of the hysteric slope, considering the whole analysis. And this is for 40% with the confining pressure increased to 100 and the CSR value 0.3. So you have a favorable property. With 30 to 40, it will be further extended. And this is the overall comparison what we are considering. Untreated specimen from 98 to 99% degree of saturation. Increasing relative density, it is having just corresponding the occurrence of liquefaction, but it is occurring after later cycle. Suppose your magnitude, the number of cycles what you are considering with respect to the magnitude of earthquake, it has happened within this zone. For example, if you take about relative density of 40, which is highlighted here, where it is taking number of cycles close to 96. Suppose the number of cycles is less than 96, 40% relative density of fully saturated soil won't liquefy. So this is the understanding with respect to the liquefaction, where you need to have more confining pressure. That means 100 kPa under saturated condition. Normally you will get this 100 kPa depth beyond 10 meter. So it's very difficult. If the depth is beyond 10 meter, the chance for liquefaction is insignificant. Suppose if you use this CSR value for the same condition to 0.4, your 96 might have been reduced to somewhere here 50 or between 50 and 70. So this is the overall understanding with respect to the liquefaction risk in terms of the earthquake magnitude. So again, these whole things has been explained in terms of hysterics loop, how you have risk with respect to how the modulus is changing with respect to number of cycles, and how it is flattened with respect to the occurrence of more number of cycles. So again, it is consolidated with the axial strain pattern for all the cases. So this is a consolidated results what you have seen. You have a problem with respect to the cyclic stress ratio. So basically, we have taken from 0.2 to 0.4. In this scenario, we have worked it out. And considering the number of cycles with respect to different degree of saturation level. If the degree of saturation level 92 to 93, what you are looking here, and 98 to 99, where the chance you are shifting from here to here for 20% relative density, the rest you are reducing from here to here. That means the number of cycles are increased and make your sample more stable. So likewise, you can see here for all other cases in terms of the cyclic mobility with respect to the liquefaction risk. So this is what finally it has been developed with respect to all the selected three relative density in terms of degree of saturation. The pore pressure ratio is plotted here. And this is final summary with respect to cyclic reaction test outcome, and where you are looking the highlighted parts are having failed in terms of double amplitude axis strain reaches to 5%. So this particular study emphasized only with respect to the accumulated air bubble, how it is really helpful into reducing the liquefaction risk. This is the overall summary. As the nitrate concentration increases, the degree of saturation decreases and pH increases, but the treated sand pH remains within the acceptable range after 5 days. Gas production rate increases, and no further desaturation is expected. So loosely saturated sample generate positive pore pressure under undrained static reaction loading. So biological desaturation degree increases the drained strength ratio by 1.5 times as the degree of saturation reduced to 90%. So reducing positive pore pressure build up. So in medium dense sample, the undrained shear strength ratio increases by 1.5 times the degree of saturation, reduction to 90%, showing the dilatation at a smaller strain and negative pore pressure at a larger strain. So we also notice the dilatancy impact on the soil. As the saturation decreases from 100 to 90, loose and medium dense, shifted to strain softening to strain hardening state, where you are expecting the dilatancy effect. Dense sand reductions from 100 to 90, the strain's hardening behavior is observed. The pore pressure ratio decreases significantly when the saturation drops to 100 to 90, reduces the pore pressure buildup regardless of sand density. So further, in case of loose sand, unsaturated sand indicates the static liquefaction, and medium sand exhibit the constructive behavior and tends to have a dilatancy effect. Temperature effect also studied, and treated sample influence and ingredient density will have more beneficial. However, increasing CSR ratio will have a negative impact. So that we have witnessed through this analysis. So finally, we have developed an interaction curve for CSR-SR curve with respect to MAPS treatment. So from that, we can able to make out the design curve. So basically, this CSR is a known one. What kind of magnitude that you are going to expect in the field? So that from that you can able to calculate the value of CSR. For that particular CSR value, what is the required SR value? That is your degree of saturation to avoid the liquefaction. So that is what our final outcome from this result. So I'll stop here. If you have any specific questions, you can ask. I'm done with my presentation. So basically, I have concentrated only on microbial-induced partial saturation. Air injection is a separate process where we have, air process also we have completed. Due to the time limitations, I could be able to present only on microbial-induced air bubbles.